Let us now look at the way in which the capacitance of a given capacitor depend upon its dimensions and the medium used. In that, number one is parallel plate. Normally we see this in labs as disk capacitors, right? Capacitor. This consists of two metallic plates of area A. Separated by a distance D with some dielectric medium with permittivity epsilon between them. These plates are of area A. Please check it. To determine the capacitance of this capacitor, we assume a charge of Q coulombs plus Q on one plate and the minus Q on the other plate with the front view. Plus Q on one plate and minus Q on the other. Q minus Q. Flux lines start normally from one plate and get terminated on the other plate also normally, traveling along through this dielectric along straight line paths. Our aim is to determine the potential difference between these two conductors. Now this is a two-terminal device. Please see, this is important for us. With a charge of Q coulombs on each plate, the field line structure or flux structure says that the field in between the plates of the capacitor within the dielectric is uniform. And the field intensity at any point, if you want the field intensity at any point, let us say this is the point, I need to draw a surface passing through this point and perpendicular to the flux lines. And that surface, if it is of area A, it cuts all the lines, because of which flux density d bar is equal to Q by AX, assuming that this is positive X direction. If it is assumed to be positive Y direction, it is plus AY. Q by AX. So the electric field intensity E bar is equal to Q by A epsilon AX. Uniform. Assuming that this is at X is equal to 0, this is at X is equal to D. One plate is at X is equal to 0, another at X is equal to D. No confusion, no. Check it once. we need to determine the potential difference between the plates of the capacitor, V is equal to minus integral d to 0, because I need to move in the direction opposite to it. Correct? D to 0 q by A epsilon AX dot dx AX. That gives me the potential to be what? Minus integral d to 0 q by A epsilon dx. Dx is x. Minus x from d to 0 is same as 0 to d with plus, which is qd by A epsilon.
Sir, why you use minus sign?
What is the potential difference, man?
Sir, difference is from D to 0.
Minus with minus d to 0, if you remove that, it will become 0 to d. It is evaluation, mathematical integral only.
Okay.
Now, V is equal to qd by A epsilon. So this capacitor will have the capacitance of C is equal to Q by V, right? C equal to Q by V is equal to epsilon A by D. So many farad. If epsilon has the unit of farad per meter, A in meter squared, and D in meter, Q by V will have the unit of farad. Actually, farad, when we defined in the beginning, it was coulomb per volt. One statement I want to repeat. If we have plus Q and minus Q on two parallel plates, irrespective of the distance between these two plates, the value of electric field intensity is Q by A epsilon. Please see this here. I am going to use it in one of the extremely important topics for us. When you go to diode, PN diode, people derive the expression, maybe so-called through Poisson's equation. But if you understand the fact that if there is plus Q and minus Q on two parallel plates, the electric field intensity in between these two plates is Q by A epsilon, irrespective of the distance between them. That's what you see. E bar is equal to Q by A epsilon only. D is not there. We can avoid a big derivation when you go to PN junction diode if you understand this fact here. Okay. Just as a change, I will do it for 2. Maybe you can continue basically this. for any number of layers of dielectric. Suppose the plates of a parallel capacitor are separated by a distance d, whereas there is a dielectric of thickness T with permittivity epsilon 1, and the remaining region, the permittivity is epsilon 2, which is D minus T. Let us determine the capacitance of this capacitor. What did I do again? Plus Q here, minus Q here. Here also, D bar is Q by A, AX. In the first region, E1 bar is, D bar is Q by AX everywhere between the plates. Everywhere. Because flux density is independent of the medium. Everywhere same D bar will be there. But in medium 1, E1 bar is Q by A epsilon 1 AX. And E2 bar is Q by A epsilon 2 AX. Anyway, we saw that electric field intensity in the previous case, when it is uniform, potential difference is just product of distance into electric field intensity. We need not integrate because it is uniform. Now, calling this Q by A epsilon as E1, this is E2 not bar. When I want to know the potential difference between these two conductors, I need to take unit positive charge. First again is T2 through a distance D minus T, then again is T1 through a distance T. Because of which the potential difference V between the plates of this capacitor is Q by A epsilon 2 D minus T plus the remaining work done. Q by A epsilon 1 T. So the capacitance of this capacitor C is equal to Q by V is what? Can you simplify and tell me the expression? This is equal to Q by A into D minus T by epsilon 2 plus T by epsilon 1 is equal to V. Q by V is A by D minus T by epsilon 2 plus T by epsilon 1. Continuing this discussion, we can say that if there is a capacitor, parallel plate capacitor with plate area A, if there is epsilon 1 over the thickness T1, epsilon 2 over the thickness T2, dash dash, right? Epsilon n over the thickness Tn, so that sigma summation Ti is equal to D. The capacitance of this capacitor is C is equal to, check it once, A by sigma summation Ti by epsilon I, correct? T1 by epsilon 1, T2 by epsilon 2, T3 by epsilon 3. Because in this case also D is equal to Q by A in magnitude. D is equal to Q by A. EI is equal to Q by A epsilon I. Potential V is equal to, just because it is the product, came out to be EI TI is equal to Q by A. EI TI is sigma summation Q TI by A epsilon I. Because of which I'll get this capacitance to be A by epsilon Ti by epsilon I. Epsilon is the permittivity. Next. Now I spoke about this because we need to know the way in which a parallel plate capacitor, if it is there, depends upon the capacitance of a parallel plate capacitor, depends on its dimensions and the medium. And the first one, simple parallel plate capacitor, whatever when we were discussing, we came across a point which is extremely important for us when I go to PN junction. Next. In fact, nowadays there are heterojunctions where we may have to use even this heterojunction solar cells or solar diodes actually are very famous for their wide spectral range of response.